Hey, this is section 8.5. In this section, we're going to talk about how clastic grains combine with chemical and biogenic sediments. Clastic grains are just individual grains. So you have pieces of rock. They have to be cemented or compacted together in order to actually turn into a rock. So generally what happens, you get biological or inorganic precipitation of cements that combine them and stick them together. So you'd have your grains and your cement that keep the rock together and actually make the clastic sedimentary rock. So if we look here, here is a clastic sedimentary rock, and if you look at it under a thin section in a microscope, so these are your grains right here, and then this brown stuff is the cement. So that was either inorganically or organically precipitated between the grains. So sediments evolve in sedimentary basins. So sediments evolve in sedimentary basins. What happens in them, unstable grains, such as olivine, pyroxene, calcium-rich plagioclase. These should be familiar from Bowen's reaction series. Amphiboles. If this doesn't sound familiar to you, you should go back and watch the weathering sections on Bowen's reaction series and what weathers out first. Become less abundant. So, through weathering and erosion, the unstable grains are being weathered out. So you're leaving behind the stable grains. Quartz, clays, muscovite, K-spar. Your book talks about K-spar as orthoclase. Unfortunately, these are two names for the same mineral. Become more abundant. So this stuff weathers out, this stuff stays behind. So you're removing this and you're keeping this. Also throughout this process, biogenic sediments accumulate and chemical sediments become more abundant. The reason being, over time, most of this happens in water. So you're going to start accumulating biogenic sediments. Also, chemical sediments are going to start precipitating out because they're becoming saturated in solution. So when you look at this figure, this is showing you, we'll start over here in the stream. Through weathering and erosion, it's dissolving ions and compounds. We'll refer back to the weathering chapter about which is more common. The clay and silt with organic particulate, because there's a lot of organics on floodplains, when the water flows over, the organics get incorporated in, and the floodplains have the clay and the silt. And you may get some other dissolved compounds that are beginning to become saturated. Over here on a beach, here's you have sand and gravel. You have dissolved ions and compounds, primarily calcium carbonate and silica. Remember chapter 21. While they're going to precipitate out and cement together, they're going to precipitate out in between the sand and gravel grains. In lake bed, you're getting clay and silt being deposited, but they also do have organic particulate. Most lakes are very rich in organics, and they're primarily clay and silt because they're fine grained, so you're accumulating your organics and your clay and silt. And also in some cases your dissolved compounds will become saturated, and they'll start precipitating out limestone and various other chert and various other compounds depending in minerals and rocks, depending on what the composition of the water is. And just remember that dissolved compounds are transported from weathering sites into sedimentary basins. So now we're going to talk about how sediments become sedimentary rocks. So sediments become rock during the sedimentary cycle. So if we look at the sedimentary cycle, which is the second picture down here, what happens is you have your magma, it's creating volcanoes, which is creating mountains, or you can have uplift and exposure of rocks due to uplift. Then you have weathering, erosion, transport. Once the sediments are deposited, then they undergo lithification, and the sedimentary rocks and either undergo these processes again, or melt to become magma, or metamorphose and become metamorphic rocks. And then the whole process starts again. So it's the lithification process that we're going to spend some time on. But a couple things that you need to know. Tectonic uplift renews the sediment cycle. Every time you have uplift of a mountain belt, you're going to have high erosion rates, weathering and erosion rates up in the mountainous regions, so that's renewing the sediment. It's providing a new source of sediment. And the tectonic uplift is associated with convergent plate boundaries. Convergent plate boundaries, you have volcanic arcs, volcanic island arcs, and or mountains being built. So that's going to produce uplift and create your mountain belts for you. Okay. So the two processes of lithification are cementation and compaction. Cementation is just like it sounds. It's when cement sticks the class together. So you have grains, water is traveling through them. Okay, so these are your grains. I'm going to label them G. So grains. The area between the grains is called pore spaces. So it's going to happen, water is going to transport through the pore spaces, and it's going to begin to precipitate out cement. So it's going to begin to precipitate out cement. And that cement is going to stick the grains together. It still may allow some pore spaces to be present, but eventually the cement will fill in the pore spaces. So it cements and sticks the grains together. So if we look at this picture, here you're looking at grains, and then the cement that's precipitating will stick and hold the grains together. So these are the pore spaces right here. These are the openings right here. Common cements are calcium carbonate and silica. Also, iron oxides. So these are three most common cements: calcium carbonate, silica, and iron oxides. So if it's iron oxide, it's going to be red. Silica varies in color, and calcium carbonate also varies in color. The second process, compaction, is when you have grains. Eventually, as things are being deposited, you get the weight of the overlying grains compacting the lower grains. So basically, this weight is going to cause these to compact and they'll become closer together. Basically, it closes pore spaces, because just by weight of overlying sediments. And this is called closest packing. It's going to pack the grains as close as it can, and it's going to close or shrink pore spaces. So if we look back at this picture down here, it's showing you sediments, they're settling, and down here, these are grains that are being cemented, and these are grains you can see down here, they're losing their pore spaces, they're becoming closest packed. When you do that, you're shrinking the pore spaces and you're going to push the water out. So it's going to push the water out of the pore spaces. So it's called dewatering. And over here, this is what's showing you uncompacted sediments, groundwater is flowing through it. In this region, it's putting some cement in, and down here, they're becoming compacted. So you can see the layers are closer and closer together. So they're actually being cemented and compacted together. So generally, lithification works with both cementation and compaction working together in this picture. However, you can have cementation without compaction, and you can have compaction where the grains are compacted enough that they actually stick together. So they can work independently or they can work together.